Hi. I'd like to share a few thoughts on making machine learning easier from, of course, the perspective of scikit-learn. So 10 years ago, we were really a bunch of computer science nerds. And these days, it seems we're an industry standard. We have, almost 1 million of monthly users, and I hear a few of you are using us. But really, we were not aiming for the enterprise. We were really aiming for ourselves, which is scientists and maybe our students, so really a bunch of geeks. And what I hear is that really it's crucial to address huge data, which is not what we had in mind. However, if you look at the size of the dataset processed, it seems a lot of data scientists are working with datasets in the gigabyte size, which is something that we can address. And the interesting thing is that this is not evolving with time. There's no clear increase. So it seems that maybe our problems are not completely different from the problems of many data scientists. So what are the real challenges to data science? Challenges faced by people. So this is an industry survey. And what we find is that the first challenge is dirty data, whatever that means. We'll maybe think about it. And the second challenge is talent. Now, another survey by Databricks shows us that the first problem people encounter is preparing and aggregating data. And the second one is exploration and iterating on it. So I think that making it easier to apply statistical modeling is something really important, is something that really addresses bottleneck of many people. So this is really what I would like to talk about, looking a bit on the some history of scikit-learn, and then things that we're currently doing to go a bit further. And our first focus was to build a toolkit for everybody and make it easy to use. The first thing we did is that we completely embraced the Python stack, which back then was a bit controversial. And the reason we chose Python was because it was interactive and easy to use, but also because it was general purpose. Now, something that was crucial is that Python was made from the start for embedding. So it has a very simple virtual machine. It doesn't have something like transactional memory management. This turns out to be quite important for us. And the other tool that we fully embraced was NumPy. So what NumPy gives us is numerical operations. But really what it is, it's a memory model, and it's a continuous memory model. And if the way I think of it is it's a fancy float star. It's a fancy pointer. So what these things give us is that they easily enable us to bridge across languages. For instance, to call performant linear algebra libraries. Or they enable a tool like Python. So Python is a language that's in between C and Python, and it's great to write high-level algorithms that still compile in a very efficient way. Now, we've, from the start, had a focus on usability. We thought a lot about API, and the driving principle behind our API is the principle of gray box. So all our models are quite interchangeable. They're defined by an interface, but they're still inspectable. You can still look at their attributes and even quite often understand their code. We have a great dedication to documentation. Improving the documentation is part of what you need to do to add a feature. And we guide our API design with examples, and these need to be easy to understand. Our goal is to teach statistical learning, not coding. And as a consequence of all this, we choose the models that we include to facilitate this. So we choose models that do not require tinkering. And we based all those choices on a huge amount of empirical testing. Now, finally, our secret weapon has really been our community. From the start, we distributed to the community development and decision-making. So that gave us manpower. We have from 25 to 50 monthly contributors, which is a pretty big team, given on top of this that people change from one month to another to bring in different expertise. But it also brought us the right focus, because people will fix and improve what's important to them. So it's fair to say that open source is one. However, it needs long-term sustainability investment. So for this reason, last year, we created a foundation for scikit-learn, where we have some sponsors who give us money to keep the project going and be ambitious. And that's really exciting for our growth. Now, speaking of growth, we're looking at addressing new challenges, and one of them is to scale a bit better, to address bigger data sets. And our focus at the beginning is algorithmic improvements. So take something as a principal component analysis. The mathematical operation underlying the principal component analysis is a matrix factorization, and it scales super linearly with the dimensions of the matrix. So it's a costly algorithm. And so one improvement that brings a lot of speed up is the randomized PCA. And just to give you an intuition, the idea is that you're going to take random fractions of the data, you're going to compute a small PCA on those fractions, and then you're going to aggregate the results in a clever way by doing a PCA across the results. And this will give, on very large data sets, this will give very large speedups, things like 10x speedup or more. Another classical model is the logistic regression. So the way the logistic regression works is the solvers is that they basically do a gradient descent on a measure of the error. And the cost here, when you have a huge amount of data, is that their gradient needs to be computed on all the observations. So it's a very costly computation. So one thing that you can do is compute the gradient on less observation. You subsample, and you randomly take those observations. This speeds up a lot, and it's called actually stochastic gradient descent. But if you don't set the learning rate right, it doesn't converge well. So it's not with our goals of easy-to-use algorithm. So there is a related algorithm that combines subsampling with a form of noise reduction. It's called SAGA, and this gives us the best of both worlds. So that's one thing that we've done in scikit-learn. And finally, something that's quite new is we address gradient-boosted trees, which are very popular. And the intuition between this model is that it's a succession of decision trees that enrich each other. And the way you can speed this up is by pre-binning the data and pre-computing histograms. And then basically building each tree is much faster. So this is a strategy that was there in XGBoost and LogGBM. And we now have it in the latest release of scikit-learn, so huge speed up. So the algorithmic improvements in general come from fitting on several subsamples and chunks and then a clever aggregation, or fitting on summary statistics. These are trends that we see. If we want to go further, at some point we're going to have to do parallel computing. And the challenge with parallel computing, say in the distributed setting, is to limit data transfer. And there are simple schemes that can do this. For instance, data parallel. I'm going to apply the same operations on different blocks of the data in parallel. Or you can be model parallel. I'm going to apply different models on the same data. So that's typically used for model selection. Now, in real life, a real machine learning pipeline is a mixture of all this. So it's a mess. So the way we work on the implementations is that for the inner loops that need to be fast, we work with very low-level building bricks, such as the OS threads or OpenMP. Now, the challenge is that these things have multiple different implementations. And because we live in an open ecosystem, we're a library, and we use library, we're going to have in the same process multiple implementations of OpenMP. So it's a very technical challenge, but it means that we need to address this, and we're working on this currently. On the other hand, we have large-scale parallelism. So the idea being that we're going to distribute the workload across different Python virtual machines and across computers. And there the challenges are transfer and synchronization. So in real life, what we have is a merry mess, which is a combination of all this, which gives us oversubscription, inefficient transfer. In a sense, this is a scheduling problem. However, because we're assembling different parts, they're not talking to a scheduler. So, and because we're a library, we do not want to embark a scheduler. So we need a simple API to address this. And we're working on this. Our basic parallel building block is really a parallel force. So it seems very simple. And it's done in JobLib. But doing it right hides a bunch of tricks. So for instance, if we're doing across a pool of multiple virtual machines, one thing that we've done is that we've made those virtual machines segfault resilient, and we're contributing some of these things back to the Python student library. We use tricks such as lazy loop consumption to avoid unrolling the loops in the memory and blowing up the memory. We might batch elements of the loop to lower the overhead. And on top of this, we're limiting the threads and the subprocesses to control the overhead. So these are technical details, but they're important. Now, the bigger picture is that we're developing behind this an extendable backend API that can delegate the scheduling or negotiate the scheduling to something else. For instance, a framework. And I really hope that soon Spark, will be able to delegate to Spark. It still is a limited abstraction because it's really a dispatch and receive queue. So if we're working across different computers, we need to serialize data, and more importantly, we need to serialize models. So these are arbitrary Python objects. And we need to serialize them, dispatch them across the network, and deserialize them. For this, we're using an internal Python mechanism that's quite core that's called pickling. And we're using a derived library that's called Cloud Pickle that is also used in PySpark. And we've been investing over the last year to improve it massively. And the two things we've done is that we've enabled subclassing the C code that does the pickling inside Python. So this makes the pickler much faster. This makes custom picklers much faster. And the other thing that we've done is that we've worked on defining a protocol for out-of-bound serialization. And the consequence of this is that we can now serialize, well, Python, not we, but Python 3.8 can now serialize without a memory copy things like a NumPy or a narrow data structure. Something that I'd like to stress is that we're now contributing these things back to Python, which means that it's an improvement not only in scikit-learn, but in the whole ecosystem. If we want to move to prediction, something that can be to production, something that can be extremely useful is the idea that we're going to represent predictors in a way that's language agnostic. And so we've been working with the Onyx team to be able to convert scikit-learn models into Onyx to be able to push them to production. And we're working on a way of guaranteeing compliance of those models. And we can work with other teams to do this, of course. So hopefully all these things will allow us to address scaling while keeping advanced algorithm, which is our priority, and also staying a library that can be used in any environment, but ideally benefits from the infrastructure. Now, the last thing I'd like to talk about is how do we bridge to data engineering? And that's not my original culture. But the reason is that dirty data, as we've seen, is a central problem. And it comes from the fact that we need to merge many different data sources. We need to deal with the input errors when we merge the data sources. And there is a bit of a culture gap between data engineering and data science, or at least statistical learning. And the reason being that data engineering is really set in databases and manipulate discrete objects like string, whereas we machine learners think in terms of numbers and in terms of arrays. And in practice, this is visible because every single machine learning academic paper starts by saying, let the data be a matrix. Or we, in scikit-learn, say, just give me an NumPy array. However, real life looks a bit more like this in the best case. So it might be a data frame. And we've got a few problems there. The first one is it's not numerical data, so it's outside of my personal comfort zone. That's true. I'm uncomfortable outside of a vector space. I guarantee you. We have missing values. That's not in a vector space, by the way. And we have non-normalized entries, which is a classical problem of databases, but I think that we can revisit them. So in terms of heterogeneous data, scikit-learn has gotten better. Recently, we now have this thing that we called a column transformer. So the idea of the column transformer is that we can apply different transformation pipelines to our different columns, choosing them on the name. And really, the idea is that we have a data frame out and a numerical array. A data frame in and a numerical array out. The benefit compared to using Python and pandas code is that it separates the fitting from the transforming. So it can be applied to new data, and it avoids data leakage. Another benefit is that we'll be able to do model selection directly on the raw data, which means that we should be able to choose the data engineering operations to maximize prediction. Now we have missing data, and as I said, they don't live in a vector space. And one classical solution to address this in statistics is to replace the missing data with plausible value. This is known as imputation. One model that we have is the constant imputation. For instance, you will replace a missing feature by a missing value by the mean of the corresponding feature. We also have conditional imputation, the idea being that you learn functions that link the different features so that when you have one missing, you can replace it as a function of the others. Now, this is a classical statistics literature. However, we're interested in prediction. And suppose that y, our target prediction, depends on whether the data is missing or not, then perfect imputation will break prediction. So one simple solution is to add a missing indicator. But what we've shown in a recent paper in my group is that if you have a constant imputation, a powerful learner will actually model the missing values. So it may be beneficial to actually use a very simple imputation model, but a very powerful learner. And this is what will be done in the next release of scikit-learn for his gradient boosting. Now, we have this problem of the non-normalized category. It's a bit of a mess. It's got typos. We can one-hot encode it, which is the standard practice, but this will blow up the dimension, and it will have problems with typos. So the standard view of this is to apply data cleaning to this, or to do feature engineering. Now, this works, but it's extremely time-consuming. The reason is you can't do this by gradient descent because it doesn't live in a vector space. So one thing that we did is that we showed that taking into account the string similarities in something like one-hot encoding actually improves prediction on many real-life problems. For instance, it addresses the problem of typos. Now, this doesn't scale well because if we do this, we still have a huge matrix. So one thing that we did is that we did a model of the substrings present in those, I call these dirty categories, present in those dirty categories. And by modeling substrings, we're modeling latent factors, and we can find so it's basically topic modeling. And so we can find prototype substrings, basically, and have loadings on those prototype substrings. So they're continuous loadings. So this is what I'm showing you here. And we can even give directly feature names. So basically, what I'm showing you here is something that looks like a one-hot encoder, but works at the substring level and learns prototype. But we see it as a plug-in replacement for a one-hot encoder. As a disclaimer, this is ongoing research. It's not as high quality as scikit-learn. So to wrap up, our focus with scikit-learn is good numerics and collaboration. We're addressing scalability via an infrastructure, but we need to couple to this And I've presented ongoing research on machine learning with dirty data, and this is what I'm most excited about these days. Thank you very much.